Now that you know all of the derivative rules, we can start applying derivatives to some more complex functions. So before we get into application problems, word problems, real life situations, we need to establish the extreme value theorem, and it's based in continuity and differentiability. So we're going to talk about what it means to be a absolute versus a local extreme value. We'll talk about that theorem. We'll see how derivatives help us to find those extrema, and then we'll finish up with the candidates test for absolute extrema. So the extreme value theorem is based on the continuity of a function, and so if f is continuous, so you have to clearly state that if you are going to cite the extreme value theorem. It also has to be a closed interval from a to b. If those two things are true, then f is guaranteed to have a maximum and a minimum value on the interval. So if you've got a closed value from a to b here on this continuous function, we've got a max and we're guaranteed to have a min. If your function is an exclusively decreasing function going from a to b, then your max will be at the left end of your interval, the min at the right. If you have a parabolic function where it's closed from a to b, the max being the vertex, and then we have two mins. We've got a min on each endpoint, and then one of them is an absolute and one of them is a local. So we have two minimums. So you're guaranteed to have at least one max or one min, but there could be more. If you've got a closed interval with a concave up function, your minimum, you have a single minimum, but you have two maxes, and again, one local and one absolute. These extreme values happen every time the derivative is either equal to 0 or undefined. So when a derivative is equal to 0, you've got horizontal tangents. When a derivative is undefined, you have a corner or a cusp or a vertical tangent. Or it could happen at the endpoints of the interval, a and b. So you have different extreme values. And again, you've got the difference between absolute and local. So here we have a maximum value, but it is local. There are no greater values nearby, but the absolute maximum happens when you have no greater values anywhere else on the function. In terms of minimums, we've got two local minimums. There are no smaller values nearby, but we have an absolute minimum where there are no smaller values anywhere, okay, overall. So these critical points happen in two ways. They happen either where f of x is equal to 0 or f of x does not exist. So when f of x equals 0, you're setting f prime equal to 0 to find the horizontal tangents. And when f prime does not exist, you're going to set f prime equal to 1 over 0, or undefined, and we're going to find either vertical tangents, or corners, or cusps. The candidates test is where you compare those values where the derivative is either equal to 0 or does not exist, and at each endpoint. That is the most commonly missed part of the candidates test. I wrote down a lot last year on quizzes and tests. Did you remember to check the endpoints? Did you remember to check the endpoints? And that's just one of those steps that kind of goes by the wayside and people forget as they get careless, that an endpoint could be a max or a min as well on that closed interval. So if you're going to find the max or the min values on this closed interval of this function, we want to do three things. One, f prime equal to 0, 2, f prime equal to 1 over 0, 3 endpoints. We want to find each of those x values and then compare their y values to determine if we've got an absolute min or an absolute max. So to find f prime, we use our power rule. We'll have 2x to the negative 1/3, in other words 2 over the cube root of x. When I set f prime of x equal to 0, there are no critical points because the numerator can't be set equal to 0. When I set f prime of x equal to 1 over 0, then I'm going to get the critical point x equals 0, which is in the interval. So now I'm going to check this critical point along with the endpoints. So what I'll do is I'll make a table and I'll check my endpoint -1, my critical point of 0, and my endpoint of 2. And so plugging in -1 into 3x to the 2/3, that's the cube root of -1 squared multiplied by 3. If I plug in 0, I'll get 0. If I plug in 2, that would be 3 times 2 to the 2/3, which is going to be less than 3. And so I've got my max compared to my min, and those are the absolutes. And then this one is local, and it is a local maximum because it's higher than 0, but it is not the highest. So I've got my absolute max and I have my absolute min. All right, to find the extreme values for this function, we're going to look for the places where, the derivative would be set equal to 0. The derivative would be undefined, and if we have any endpoints. Now, one thing about endpoints, so I want to look back at the domain of this problem, and because it's got a square root in the denominator, and because it's the quantity 9 minus x squared, we can't have 0, and we cannot be negative. So my domain is limited between 3 and -3. All right, let's find the derivative. So my derivative would be -1/2 times the quantity 9 minus x squared to the -3/2, and then times the chain rule of -2x. So overall, we're looking at a positive x in my numerator, and then 2 times 9 minus x squared to the 3/2 in the denominator. When I set the derivative equal to 0, that's going to give me the critical value x equals 0. And when I set the derivative equal to undefined, that's going to give me the critical values x is plus or minus 3. But because that's not even in the domain of the problem, I don't have I don't have endpoints, and so then I have no endpoints to work with. So I really only have one critical value. The function then, now I know -3 isn't in the domain, but we can plug in something greater than -3, and then 0, and then we can't plug in 3 itself, but we could plug in something that's a little bit less than 3. So if we plug in 0 itself, we're going to get the value 1/3. And if we check the endpoints, we're going to get positive infinity. And so clearly 1/3 is the smallest value, so we're approaching infinity on either end, but we've got 1/3 as the smallest y value, so this would be our absolute minimum. So to summarize, make sure you always set the derivatives equal, first of all, establish continuity, then set the derivatives equal to 0 and undefined, and don't forget to check the endpoints of the interval if there are endpoints so that you can determine the absolute values of your extrema. Other things to watch out for are whether the question is asking you for the absolute value itself, which is the y value, or if they're asking you at which x it would occur. So those can be two similar solution strategies, but different answers. Are you answering the x value, or are you answering the y value? I'm looking forward to seeing you guys on Tuesday during our Zoom meeting. I hope you have a good start to your week.